Associated to every linear map are two subspaces called the kernel and the image of that linear map. We're going to define them in this video, see some examples, and prove that they really are subspaces. So let's begin with a lemma, which we'll use a couple of times, which is that if you have a linear map from a vector space V to a vector space W, then it sends the 0 vector in V to the 0 vector in W. So we'll do the proof, which is nice and easy. So if we look at T of the 0 vector in V, well, the 0 vector in V is the same as the 0 vector in V plus the 0 vector in V. So I'm free to write that if I like. And then I can use linearity. So the linearity condition tells me that this is the same as T of 0V plus T of 0V. Okay, and now I'm going to subtract T of 0V from both sides. So on the left-hand side, I should have T of 0V minus T of 0V. So that's the 0 vector. But where is it the 0 vector? It's the 0 vector in W, because we're talking here about things in the image of T. Those things are elements of W. And on the right, I will have T of 0V plus T of 0V minus T of 0V. So one of them cancels out, and what you've got is this. Okay, that's the result that we wanted to prove. So every linear map has to send 0 to 0. So just to revisit the example that we saw at the end of the last video of a non-linear function, we had t from the real numbers to the real numbers given by t of x was 2x plus 1. Then t of the 0 vector in the real numbers, that's just the number 0, well, that would be 1, and that's not equal to 0. So we could have said straight away, because t of 0 is not equal to 0, t is not linear. And this is a sometimes useful way to rule out a certain function being linear. If it doesn't send the 0 vector to the 0 vector, it cannot be a linear map. So we're now going to define the kernel of a linear map. A kernel of a linear map T from a vector space V to a vector space W, which we write like this, is defined to be the set of all elements of V which T maps to the 0 vector in W. So as an example of this, let's take, we had a differentiation example. Let's look at that one. So we had D, which was a function from the set of polynomials in one real variable x, to the same thing defined by d of f is just the derivative df by dx. So what is the kernel of D? Well, that's all the polynomials f whose derivative is 0. But a polynomial has derivative the 0 function if and only if it's a constant polynomial. So this will be all the constant polynomials. So another way we might write that is as the span of the constant polynomial 1, like this. Okay, there's an example of the kernel of a linear map. Let's take another one. Let's take a generic example. So I'm going to take A to be an M by N matrix. And I'm going to take TA to be the linear map from, let's say, the entries of A are from R. And then we can think about a map TA from R to the N to R to the M, defined by, as usual, T subscript A of X is just A times X. Then what is the kernel? Well, we've met the kernel of this before. The kernel of TA is all things, let's say, X in R to the N, such that TA of X is the 0 vector. In this case it will be the 0 vector in R to the M. So that is, of course, the null space of A, because what you've got here is just A times X equal to 0. So by definition, this is the null space of A. So there's an example of the kernel of a generic linear map. Let's look at another one. So finally, let's take a concrete example. So let's take F from the 2x2 real matrices to the 2x2 real matrices, defined by F is going to be the transpose function, so f of A is A transpose. Then Ker of F would be all the matrices A such that A transpose is the 0 matrix, so the 2x2 0 matrix. But if you transpose a matrix, you can never turn that matrix into the 0 matrix unless you had the 0 matrix to start off with. So in this example, the kernel of F would just consist of the single element, the 2x2 0 matrix. Okay, so kernels are a concept that we've seen before, and they're something which we can compute in examples like this. Let's now look at the other subspace we were talking about, which was the image of a linear map. But the image of a linear map just has the ordinary meaning of image, which we've met before in chapter 2 when we talked about the image of a function. So this is exactly the same definition, just we're just happening to think about linear maps only this time. So the image of a linear map T from V to W, which we write like this, is just the set of all things which you can get by doing T to something in V. So I won't do as many examples as this time because this is a concept that we've already met several times, but let's just think about a couple of them. So we'll go back to our matrix multiplication example. So we'll take A to be a M by N, let's say complex matrix this time, and then we get a map which we'll call TA from C to the N to C to the M. As usual, TA of a vector is A times that vector. Well, then what can we say about the image this time? You actually have seen the image before. So image of TA is, well, it's the set of all things TA of X for X in C to the N. So this is the column space of A. It's the set of all linear combinations of the columns of the matrix A, or the span of the columns of the matrix A. So we proved in our lectures about matrix multiplication that when you multiply a matrix into a column vector, the result is a linear combination of the columns of that matrix. So let's just remind you of what the meaning of this symbol was, the column space of A, and that is the set of all linear combinations of the columns of A. As another, let's take another example of the image of a linear map. So we could take, for example, let's take our differentiation example. So we have D, we'll take a slightly different differentiation example. So D of R less than or equal to N of X to the same thing. So remember, R less than or equal to N of X means all polynomials of degree at most N. So real polynomials of degree less than or equal to N, then as usual, D of F will be the derivative, dF by dx. This makes sense. It really does map a polynomial of degree at most n to another polynomial whose degree will be at most n, because when you differentiate, the degree goes down or stays the same. So what would the image be? Well, I'll tell you the answer, but I won't prove it for you. You should think about how to prove this yourself. The answer is you can get any polynomial of degree at most n minus 1. So in fact, the image of D is a0 plus a1x plus up to a n minus 1 x to the n minus 1 for a0 up to an minus 1 any real number. So it's clear that the image of D is contained in this set, because when you differentiate, the degree goes down by 1. So if you differentiate a polynomial of degree at most n, the result is a polynomial of degree at most n minus 1. So that tells you that the image is contained in this, but in fact it's equal to this. Okay, so that's the image. Let's now finally prove what I said, or at least part of what I said earlier, which was that the kernel and the image of a linear map are in fact subspaces. So if you have a linear map T from V to W, the kernel is a subspace of V, and the image is a subspace of W. So we'll do the proof for the kernel. So we have to prove that the kernel passes the subspace test. It's got to pass all 3 conditions for being a subspace. So part 1, I've got to show that the kernel contains the 0 vector. Well, if you take T of the 0 vector in V, then you know that's the 0 vector in W by the result we proved on the first slide in this video. So what that tells you is that the 0 vector in V is in the kernel of T. Remember, the kernel is all the things which T sends to the 0 vector in W. So this tells you that T sends the 0 vector in V to the 0 vector in W, and therefore the 0 vector in V belongs to the kernel. So that's the first part of being a subspace. You've got to contain the 0 vector. Part 2 of being a subspace is you have to be closed under addition. So let's let X and Y be elements of the kernel of T, and I have to show that X plus Y is also in the kernel of T. So to check that, let's just look at what T does to X plus Y. Well, because T is linear, that's the same as T of X plus T of Y. That's the second part of the definition of linearity. But since X is in the kernel, that's the 0 vector. And since Y is in the kernel, that's the 0 vector as well. So what we have is 0 W again. If you add the 0 vector to itself, you get the 0 vector again. So X plus Y is in the kernel of T. We've shown that the kernel is closed under addition. So for the final part of the definition of being a subspace, let's let well, I need to say what field I'm working over. In fact, I can kind of dodge that. So let's let lambda be a scalar, which means an element of whatever field V and W are vector spaces over, and let X be an element of the kernel of T. Then I have to show that lambda times X is again an element of the kernel of T. So T of lambda times X, well, we can just use the definition of linearity again. So part 1 of the definition of T being a linear function is that T of lambda X is lambda times T of X. So this is lambda times the 0 vector in W, because X was an element of the kernel of T. So that is the 0 vector again. Okay, we've proved the kernel contains the 0 vector, we've proved it's closed under addition, and we've proved it's closed under scalar multiplication, therefore the kernel is a subspace. You should have a go at proving the image is a subspace yourself. If you want to check your answer, you can find it written up carefully in the lecture notes for this section.